Thank you, Alejandro, and thanks to all of the organizers for this really wonderful workshop and for the invitation, and also for the long program, which I've gotten to participate in. So I'm going to take the opportunity to talk about some joint work with Guillaume Chapuy, who is my PhD advisor, and Baptiste Louf, who's another one of his former students, from a couple of years ago, which is on random partitions. I always struggle a bit, actually, with the title of this, because I will really be talking about random partitions, but the motivation for why we study them under the particular probability law that we choose comes from different combinatorial objects, and in particular ones with some topology. So this is where genus comes into things. And here's a bit of a plan. I'll start by introducing the combinatorial objects we'll talk about. On the one hand, there's something that exists in the symmetric group, but on the other side, they're also discrete surfaces called maps. And in that sense, we'll have a sense of topology. But from that, I'll then define a measure on partitions. And the main results I'll present afterwards will really be concerned with that measure. And only after presenting them will I say something about the original problem I started out with. So to start, the kind of combinatorial side that we're starting with is the counting of transposition factorisations on symmetric groups. So if we are on the symmetric group of order m, and we're going to be interested in factorisations of the identity by L transposition, so L elements that exchange elements that exchange two labels. And these have, for a long time, been studied in the context of enumerative geometry. This goes back to Hurwitz, like 1891. Hurwitz found that these were in bijection with certain branch coverings of the Riemann sphere. But we can also see the geometry of these in a more discrete way using a construction called pure Hurwitz maps, which is directly related to the complex geometry version as well. But I'll focus purely on the discrete case. So starting from a factorization by some L transposition, so I'll say tau 1, tau 2, up to tau L of the identity on Sn, the map we construct will look like this. It'll have n labeled vertices, and it'll have L labeled edges. Right, n's the order of the group, and L's just the number of transpositions in the factorization. And when we have a transposition which exchanges the vertices A and B, that just means we're going to draw the edge with the label of that transposition between them. And now we have an extra constraint as well. We can't just draw the edges anywhere we want. It's not just a graph. We also have an orientation of edges around each vertex. So we'll have it that the edges increase in counterclockwise order around each vertex. So just to do this for a very simple case, say on S4, we can, I'll go even simpler. I'll go on S2 and L4. We only have one choice. We can factorize the identity by 4 copies of the transposition 1, 2. And the way we draw this is just we take, on the vertex labeled 1, we'll take the edge labeled 1, and the edge labeled 2 here, the edge labeled 3, and the edge labeled 4. And now we just need to have them arrive correctly, all of them, at vertex labeled 2. Oh, sorry. So we'll go 1, 2, 3, 4, and the other one. We want them to just arrive in the right order. So here, sorry, I should have drawn this differently. So here we'll want this one to come under. This one we want to come back in here. And this one want to come around like this. So it's something very simple, but we can see that we can't draw it on the plane. So this has some higher genus. We can say that there's a topology associated with the simplest surface we can draw on. In this case, we can see that if you just introduce one hole here, you can draw it on a donut, so a surface of genus 1. And in general, every time we construct something like this, we map a transposition factorization to a map, a pure Hurwitz map of this kind, we'll be able to identify it with this kind of surface divided into faces. But I should note, in my definition, so when we're considering the set of factorizations of the identity by transpositions, we're not going to require the factorizations to be transitive. So we can just have transpositions from some subgroup of the symmetric group. And that means we can have some vertices isolated. We can have separate connected components. We don't just have one surface. We really just have, for a generic transposition factorization, we have a collection of graphs with these orientations that are defining discrete surfaces. And the data that we have here is also enough to say what the genus is. So here we could see it's 1, but we can read it off really any transposition factorization. Because we can rely on the Euler characteristic formula. This says that the Euler characteristic is just the number of vertices minus the number of edges plus the number of faces. So we know we have n vertices from the order of the symmetric group minus L edges. And then for the number of faces, actually, this is also going to be n because we said that it's the transpositions multiplied to give the identity. And that actually is what determines how the edges map around each face. So what this tells you is each face will have exactly one descent in the edge labels on it. So here in the example I've drawn, so we've got 4 edges. So there's one point here where it goes from 4 to 1, this edge label descent, which we can mark. Here we go, so 4 to 1 is here. Is it? I think. No, I'm sorry, 4 to 1 is here. And here I've identified actually each of the 2 faces. If you continue to color in along this torus from either one of these, you won't direct. The edges have cut these into 2 different faces. So really this is a type of gluing of polygons if we're on a single connected surface, but more generally it's gluings of polygons any way you want to form a collection of surfaces. So rather than just having what we'd normally have for a connected surface, which is 2 minus 2 times the genus, we have 2 times the number of connected components minus 2 times the sum of their genuses. So here's an example. Unfortunately, I cut it off, but I know that it's 16 transposition, factorization by 16 transpositions on S9. So you can add it up. That's 2 times 9 is 18 minus 16 gives you 2. So it's, if you were to make a single surface, this would be planar. But because we have a non-transitive factorization, we can't, for instance, construct from the set of transpositions any element of the symmetric group with 7 in it. Then we see that we actually have things of higher genus appearing. So really it's, if we think of the Euler characteristic, it's 2 minus, I guess, the minimum genus, or 2 times the number of connected components minus the sum of the genuses. Now, the reason that we would study these types of objects in particular, in a broader sense, is largely due to combinatorial interest. This happens to be just one of a large universality class of objects, which can model, for instance, quantizations of space-time and other things in physics, but also just generally have very fascinating shared properties. So more naturally, if we think of a map as this kind of just collection of combinatorial data, we might want to just take certain polygons of a given index, and glue them together, look at quadrangulations or triangulations. In other words, divide surfaces into faces of certain degree, or indeed look at how to embed a bipartite graph into a surface. But when you look at how these behave asymptotically, so when the size, either the number of vertices or number of faces, goes to infinity, we see the same properties. So in particular, if you look at rooted connected maps, you have the same asymptotic exponents. You always have the size to the power of minus 5/2 times the genus minus 1 if you fix the genus. But also in a probabilistic sense, there is some universality. So if you take a uniform random element of any of these families, the kind of classical case, triangulations, quadrangulations, etc., you can define a scaling limit for what that object looks like, which is a random metric space. And it so happens that although this is a much less natural construction coming from the symmetric group, when you look at transposition factorizations, actually it shares these properties. Certainly it shares the asymptotic enumeration at fixed genus. And we're almost certain it shares the same scaling limits, because in a paper by Enrique Duque, Dominique Pourin and Julie Schaeffer, they showed that there was a similar bijection with maps that are then eventually used to prove convergence to a metric space. Or with trees, rather, sorry. Trees. So in the fixed genus case, it's very well understood how these kinds of objects behave. But in the high genus case, where as the size of a map, so the number of vertices or the number of faces grows, the genus grows as well, things are much less well understood. And actually, this is a very different situation because, for instance, the local geometry around a vertex is no longer the same. Instead of looking locally planar in this kind of a large uniform random map, you see some hyperbolic geometry locally. And it was only recently that Thomas Budzinski and Baptiste Louf found the first estimate for how to enumerate objects of these kinds in this regime. So they worked on triangulations, so divisions of surfaces of genus G into degree 3 faces. And they showed that if, as the number of faces n goes to infinity, the genus scales like some theta to the n, then the number of these triangulations will scale like n to the power of twice the genus times an exponential function with a known factor plus some polynomial term that they don't know. So this is a much less fine asymptotic estimate than we have in lower genus cases, but it's also a much more complicated problem because these objects are counted, for instance, by, in general, maps are counted by matrix models, things that have natural topological expansions. So where we try to access high genus is we really don't have the methods you'd normally have of expanding and looking at the low genus terms. So the methods used by Thomas and Baptiste in this paper are really very different. They used an entirely probabilistic approach. And this regime is really what we wanted to try to understand coming from a different perspective. And the reason that we chose Hurwitz maps is because we can define them in terms of transposition factorizations, and as a consequence, we can count them with partitions. So again, I'll just emphasize we're in the using, sorry, there should be a number. It's not the set. H and L should be the number of transposition factorizations there. This number is not counting connected objects as we'd normally look at for maps. But because it's counting these stems on symmetric groups, the representation theory gives us an approach, specifically gives us Frobenius' formula, which lets us write this as a sum over partitions, given here. So really, the partitions are playing the role of the conjugacy classes of the symmetric group of order n. When we will take a sum of this term f lambda, which is either the dimension of, really here it's more the irreducible representations more accurately. So f lambda is the dimension of the irreducible representation indexed by lambda, and c lambda is just the character, the renormalized character of a transposition on that that representation. But these are also things we can just read off a Young diagram. So for the Young diagram lambda, so here I use French convention. I put lambda 1 on the bottom and lambda 2 boxes next, and so on. F lambda is just the number of standard Young tableau shaped lambda, so the number of fillings from increasing left to right and bottom to top in this convention. And we can compute this using a hook length formula, for instance. And C lambda is the sum of the contents. So the contents is of a box in this is just a measure of how far it is from the diagonal. So here we have, the more we are to the right, we are positive. It's just the coordinate j minus I, j minus I in this convention. And we can see that if a partition is self-conjugate, it's not going to contribute to this sum at all. It's only for things with some asymmetry under conjugation that we have some contents. All right, and these are also, it's unsurprising that this is something that's proven with the Jussius-Murphy's elements. Like anytime content sum appears, it's like this. But for the sake of this talk, or for our work, this was really just a kind of a black box. Yeah?
So I have a question. Maybe in the previous result with high genus, so one cannot use these formulas for high genus are not so good. Or is it because of the connected part, or because?
Sorry, yeah, this is for the connected part. So this is where this is truly the genus of an object. But here we don't know exactly. Yeah. And also, I should say that this is only really proven for one model, unlike other fixed genus enumerations. So I think that it's very well conjectured that they've done something for other p angulations, but the universality of this is slightly less clear as well. Oh, sorry. So say we want to look at these numbers in a high genus regime. The question is, what approach can we have? So on one hand, you can turn to integrability. In fact, there's a very natural link between this kind of formula and tau functions of the total lattice hierarchy. This is found by Okunkov. And this means that there's a way of computing classical Hurwitz numbers. So these are the connected ones. So not things with this formula, but where you only are counting connected components. But for us to look at the asymptotics in a high genus regime, in fact, this won't help us. So being able to compute things in polynomial time at fixed genus isn't exactly what we need. But at the same time, this is something that looks a bit like things we've seen in integrable probability. And it kind of looks like it's very natural to just read this as a probability measure. Because if you take any n and you have an even L, there is a way of factorizing, and the L is positive. They're actually not even positive. there is a way of factorizing the identity into transpositions. That means these are positive integers. It's kind of trivial. But also, because the L is appearing in the exponent of the content there is even though there's a sign on the content, here, anytime it's giving something non-zero, actually every partition has a positive contribution, or a non-negative contribution, rather. So that means we can just reread this as the normalization of some probability measure, which we define as the Plancherel Hurwitz measure. And the reason for the name is if we remove the content sum part, we just get back a classical measure, the Plancherel measure of partitions of n. So this is what we'll study, and I'll go back to that classic case first of when we just set L equal to 0. So at the level of Hurwitz numbers, this is completely trivial. There's one way of factorizing into no transpositions. And this is just the statement that the sum of the numbers of the F lambda, the numbers of standard Young tableau squared over all partitions of n is equal to n factorial. And from this, we just read off the usual Plancherel measure. But although it's trivial for the Hurwitz numbers, it's obviously a very rich measure. In particular, we can look at the limit behavior we see from it as n tends to infinity. Here, I've just sampled some partitions under this to show what it looks like. So what we see is the larger you take n to be, the more, when you can see the whole, you zoom out enough to see the whole Young diagram, you see the same shape. Oh, sorry. And this was proven by Vershikirov and then independently Logan and Chap. And we can state it like this, that we have a convergence in probability of a piecewise linear curve, which follows the top of the Young tableau, of the Young diagram, once we've rotated it by 45 degrees and put it in some renormalized coordinates so that the area is always the same of this Young diagram. This converges in probability to a limiting curve, which I write omega here. And moreover, we also have a convergence in probability of the first part when renormalized by root n to 2. So this is something that we're using supreme norm here, this is something that you wouldn't see just from the limit shape, the fact that we actually have a law of large numbers for the statistic lambda 1, the largest part of the partition. Oh, sorry. But that statistic lambda 1 is something with a very natural interpretation. It's particularly interesting that we have that. So remind you that this, in the case of the classical Plancherel measure, we have this interpretation in terms of uniform random permutations on a symmetric group of order n when we're looking at partitions, Plancherel random partitions of n, where because the Robinson-Shensteg algorithm will bijectively map every permutation to a pair of standard Young tableau of the same shape lambda, in such a way that the parts of the shape encode the increasing subsequences, we have that, the first part of a partition under a Plancherel measure is equivalent in law to the length longest increasing subsequence of a uniform random permutation. So really, when we look at this limit shape, even if we forget the rest, just this behavior of this first part says something about, say, we take a kind of a uniform set of points on space given by a partition or by a permutation, what the left, what the up and right path through that will look like, the longest choice we can make will look like, at least to show that it converges in probability to 2 root n. And this is also a case where we have this kind of integrable probability methodology. So if you add a bit more randomness in this situation, so you instead of taking a measure on partitions of n, you take a measure on all partitions, which corresponds to the case where you've randomized the size to be a Poisson random variable. Then, in fact, they define a determinantal point process. So when we look at these sets, which you get by reading the downward slopes of the tilted Young diagram off, we can express the probability of finding any point in those as a determinant of a known kernel. And this leads to really, really fine information. You can say that there's a local limit given by a sign process. You can say, in particular, and this applies also to the non-Poissonized case, that you have Tracy-Udom GUE fluctuation of the edge, so a universal distribution coming from random matrix theory. And really anything you'd want to compute about a partition under this measure, we can compute very explicitly. Now to switch things a bit, there's another simple case which is not trivial, really, for the Hurwitz numbers. Yeah.
Show again the definition of the measure.
Yeah.
Sorry, with L. There. Awesome. Thank you.
Yeah. Sorry, no, I should have had it sooner. Yeah. So sorry, it's just every time I might just write it down.
Are the C lambdas always positive?
Sorry, when we only take L to be even, so C lambda to the L is always positive. That's the contribution. And yeah, in the case where L is odd, the conjugate partition is always compensating exactly. So that's why we always get, it's quite intuitive that we should get Hurwitz number of 0. So I'll just. So yes, the next case I'd like to mention is the other simple case, which is just if L is really, really large. Because if we take L to be large enough, then if we were to take any product of L transpositions, we can expect it to be well mixed and to be uniformly sampled among partitions of the same parity as L. So what we can conclude from that is that the probability that when we have taken L to be even, that we've hit the identity should just be 2 over n factorial. There's n factorial over 2 even parity permutations. And as a consequence, we can approximate the number of transposition factorizations just by taking this probability times the total number of transposition factorizations. So the number of transposition factorizations with L transpositions, or not factorizations, sorry. These aren't factorizations, these are just products. The number of products of L transpositions on Sn is just n choose 2 to the power of L. And actually, if we look back at this, we see that really this is just the contribution from 2 partitions, because if we take a partition that's all in one row, or indeed just one column, the content of this is just 1, 0, and then 1, and so on, up until if there's n terms, we have n minus 1. So that's just n choose 2, the content, summed, the sum of the contents. And the number of standard Young tableau of such a partition is just 1. So we have the contribution of this one, and then we also have the contribution of this one, which it's a negative content sum, but it appears with a power of L. And together, they give us everything we need for what we should have as the Hurwitz number in this regime.
So is this, can I maybe say, is it because bigger contents win you because L is large? Is that right?
Yeah, so it's not surprising. You know that there's going to be, at some stage, some way that the contents, if you take L very big, the contents will dominate. And that's what happens. And we know also when it happens because there's this famous result by Diogenes and Shashahani, where they showed that if you take a transposition random walk on such a group of order n, L steps, then the mixing threshold is when L is greater than a half n log n. So what we'll be interested in is something between the two. So if we take these two regimes to be, on the one hand, trivial for Hurwitz numbers, but interesting for partitions, and here it's like interesting a bit for Hurwitz numbers, but very trivial for partitions. We want something that's hopefully interesting for both. And this is what we find. So we looked at a linear regime, so one completely analogous to what Budinsky and Louf studied. So here, for us, the genus is controlled just by L. So I say genus, but really I mean negative Euler characteristic. We're taking a large negative linear Euler characteristic in the number of vertices. And so in order to define our results, we'll just lift a bit of degeneracy because we always have the same measure on conjugate partitions. So we'll only look at the positive part. We'll just reduce to the part where the content sum is positive, project onto that half. We're taking L to be strictly greater than 0, so all of the self-conjugate partitions are contributing nothing. So this is no problem. And what we find then is that as n tends to infinity, we have a kind of limit phenomenon on two completely different scales. So the first part scales as 2 times L divided by log n. So really just faster than any power of n that's less than 1. And then as for the rest, we will just call this partition lambda tilde will just be lambda 2 and so on. That has the same Verschach-Kirov-Logan and Shep limit shape with the same scaling. So it's scaling everywhere like root n. And we also have a convergence in probability for the first part of this partition, lambda tilde, or for lambda 2, to root n. So really, we're just seeing from afar a random partition under Plancherel plus this much, much bigger first part. Sorry. And I wanted to give some ideas of the proof because
sorry, one more thing. So when you just take extreme random partition with Plancherel and just one single alpha, there is the same kind of limit shape. Even though the leg grows like n, but not n over log n.
Yes.
It's the only difference.
Yes.
Yes.
What is alpha?
Just kind of specialization of the measure. Anyway.
Yeah. So
there are random partitions that look like that.
Yeah. We don't have like a connection to them. Yeah. But yeah. This is coming from somewhere else, I guess. I don't think you can explain that formula into its contents, but maybe there is something more. I'm not sure. So yeah. So just I would like to say a bit about how we prove this because that's where the effort went really, and also I think it is something very non-trivial to try to say something about a random object when you don't know what the normalization is. Really, what we're looking to find is the normalization of the measure by studying elements under it. So it's maybe a little bit of an odd way to work, but we can do something because we can just compare entropies. And we do this kind of on two scales, because it's a sort of two-scale limit. So first, at the macroscopic level, we're really just by comparing the two entropies, coming on the one hand from really the term that's identical to the Plancherel measure, the f lambda squared divided by n factorial. This looks like a Hooke integral. So really just an integral over this curve here that we write in renormalized coordinates. And on the other hand, we obviously have some simple expression for the content sum just by taking binomial, or like lambda I choose 2 and shifting it and summing it up. So first, what we do is we have to split into two regimes. So say, like, what are the parts of a partition that will be, or how much of the partition will be on the large scale, so scaling faster than n to some power, less than 1, and what will be scaling slower than that. And we do this very coarsely. We just take n to the 1 minus epsilon, where epsilon, we can just fix it to be 1 over 100. And then we'll look at lambda to be the parts of lambda plus, which are greater than n to the 1 minus epsilon, and lambda minus, which are less than that. And then we can put an upper bound very easily on probability. We have a lower bound on the normalization just from plugging in what we know will be the limit shape, and looking at what that gives. That's one partition, which is enough to kind of lower bound it. And then we get a nice enough expression for an upper bound that we can see, okay, this is some function of so the size of the partition, the sum of the parts of the partition which are greater than n to the 1 minus epsilon times log n divided by L. And this is something that has a maximum and is negative anywhere else. And as a consequence, we show that this size of lambda plus has to be in some interval. After that, we say, well, how many parts are there in this? But to do so, we can actually just limit our attention. We've shown that it's exponentially improbable. We've got an exponential bound on the measure on anything that escapes that. So we can really just limit our attention to partitions with a first part in this box, or a giant part, a big part with, is what we were calling it, with all parts greater than n to the 1 minus epsilon. And how we can do this is really just by comparing what happens when you have more than one part and when you have another. So if you say that you have some other, so some m boxes are not in the first part, we can compute how many or what the contribution of those partitions will be, and then count how many other ways those boxes can be filtered, can be moved onto the first part. And as a consequence, this comparison shows us that actually, really, there can only be one big part, because it costs too much to make another part that's big to the kind of the content sum contribution. And we do the same thing to show that actually nothing escapes on the other side. That we don't have a large number of parts either. We have less than n to the 1 minus epsilon parts. Then from that, we can see what the limit shape looks like on a large scale. We can just really optimize with a little bit finer expressions. We can limit ourselves to this kind of partition. We can use explicitly this Hook length integral to see that this thing is really just optimized when we have lambda 1 scaling as L over log n, and we have the rest just doing whatever is needed to do to minimize this Hook integral. And we know what does that. It's the Virchow-Logan-Shepp limit shape. So that's exactly what this looks like on a large scale. What we haven't shown, though, is what lambda 2 does. For now, we've only bounded it by n to the 1 minus epsilon. But we can do something with that by going by steps. So first, we use a kind of approximation of the Plancherel growth process, where we remove, we say something about the law of lambda 2 by comparing it with the same partition with that part just completely removed. There's actually, so here we're just fixing the first part to be the right first part, so it's a capital L in this notation. And we only move boxes in the rest of the partition. And this actually gives us a good enough, this actually gives us a good enough estimate to say that lambda 2 will scale, can't go any faster than e times root n, because if here in this formula k is anything greater than e, we have something that's suppressed exponentially. And from that, we have enough to use some other results. So we can rely on a large deviation principle for the first part under the classical Plancherel measure to show that what we have is just a bound of 2 to 2 by root n. So just to recall this is our main result. And now I'd like to say how we can interpret it, because we no longer know what this means in terms of, we don't have an RSK bijection. We can't say what lambda 1 is, we can't say what lambda 2 is. But we'd actually started by talking about Hurwitz numbers, and this is enough for us to estimate Hurwitz numbers, classical unconnected Hurwitz numbers. What we get is the following. We get that in the regime, the regime where L grows linearly in L, we have that H in L is equal to L over log n to the power of 2L by exponent of something, so minus 2 plus log 2L plus something else. So we have other polynomial terms that we don't know. This is very much an approximation. But in principle, it's as strong as the approximation that Baptiste and Louf obtained, except that it's not really, because it's counting something very different. So we don't know how to we don't know how to compare the two, because HL count, on the one hand, labeled objects. We have labels on the edges and vertices that we wouldn't normally have in a map, but also they count objects that aren't necessarily connected. So in order to really compare them, I think it is necessary to at least look at the second point. Are we looking at something connected? And this we can do in a probabilistic way. We can say if we were to look at the random, uniform random unconnected maps here, do they have a giant component? And the answer is they have a giant component in edges. So all of the edges concentrate, or not all, a number that grows linearly with the edges, the number of edges concentrates to one part, but that part doesn't have a linear number of vertices. So really, we're not seeing any linear genus connected components appearing. And just to say how we can show it, the first result is quite simple to see from what we did before. If you want to say, are the vertices in a giant component, is there like a linear n number of vertices that are connected to something, we can just say, how many isolated vertices are there? We take a uniform random map and we look at just one vertex. The probability that it's going to be isolated is just going to be the number of Hurwitz maps with one less vertex, hn minus 1l, divided by the number of maps that we're in at the moment. And this we've actually already kind of given an estimate for in the kind of microscopic elements of the proof. So we know actually from what we did before to compare partitions that actually it's with probability 1 plus something quite small, and that we have a linear number. We have n minus something that scales like n over log n isolated vertices in this map. So just to conclude, I'd like to mention the things we don't understand. So obviously the first thing is we found something kind of interesting in lambda 1 and lambda 2, but we've lost the meaning of lambda 1 and lambda 2 that we would have for a Plancherel random partition. So really we can ask, what does it mean? The most obvious thing to me in terms of our results, what it can mean, it's something to do with the size of the connected components. So this kind of n over log n or L over log n vertices that can appear in edgewise giant component, that possibly relates to the size of the first part. But also, I mean, the real fundamental question is there a bijective proof for Frobenius's formula? So in the L equal 2 case, so here the Hurwitz numbers are just n choose 2. This has been bijective proof has been given by Wenji Fang. He used jus de Taquin, but this is a signed bijection, which doesn't generalize very, very easily. So it would be nice to see what more you can do. And then there's also, okay, this is, so Leo did give an example. It's another thing to do is to compare with other models that give the same limit behavior. One found by bijection by Slim Kamoun is you just condition a uniform permutation to have a certain scaling of fixed points, then you can get the same kind of shape. And because he used this kind of, he could use some universality results and say that the fluctuations in lambda 1 are Gaussian, and if the number of fixed points, so you condition lambda 1 really to just be very big, and they're going faster than root n, and if they're smaller, then you still have this Tracy-Wood MGUE statistics. So that's another thing to ask is, can we really find the law of lambda 1? And then the next thing is, of course, can we say what happens for every other range of L? We've only studied one regime, and a particularly interesting thing would be if we can make L go a bit slower than linear, maybe we can actually get giant components where the number of edges is linear in the number of sides in that component, because now we've only got these kind of super high genus components. And in general, the kind of natural phase transition to look at is n to a half. And this is related also to work by Philippe Bian, where new fluctuations were found. So it was coming from a Scherval correspondence, so it's not really the same measure, but we can conjecture that maybe the same effects could appear. And then, of course, the other question is, can we say something about a determinantal point process? And can we find these kind of rich information you have for the normal Poisson-Plancherel measure? It looks like you can, because you can write this as an expectation of a wedge space. But when you try to commute things, things are difficult. So far, I've tried it. It's not been tractable, but hopefully there's some method where you can get much more fine information from these measures. So thanks for your attention.